Okay guys, so let's take a look at this voltage sampling and mixing, right? So if we, let's say we need to measure a voltage, right? So we need to measure a voltage across some resistor, let's say. So if we want to measure this voltage, what we'll do here is we have to connect a voltmeter. So when we connect the voltmeter, what we do is we connect it parallel to the load, right? So this is voltage sampling. That means we are taking the voltage across this resistor out. So therefore, you can see that voltage sampling has to be done parallel to the load, right? And similarly, voltage mixing. So if we want to add a voltage to another voltage, we have to connect the two voltage sources in series, right? In series, like this. So then our resulting voltage will be V1 plus V2, right? So therefore the voltage mixing has to be done in series, right? Okay, now current sampling and mixing. So similar to the previous case, let's say that we want to measure the current going through a resistor, right? So if we want to measure the current going through this resistor RL, what we need to do is we need to connect an ammeter. So we connect the ammeter series to this voltage. So therefore current sampling has to be done in series, right? And what about current mixing? So let's say there is a current source giving some current I1, and suppose that we want to inject more current into this. So that means we have to mix the current. So to mix the current, if we want to mix the current, we need to connect another current source in parallel to this current source, right? So this is current mixing, and it has to be done parallelly or in a shunt configuration. Okay, so having known about that sampling and mixing of current and voltage, let's move to the basic feedback topology. So there are four topologies for basic feedback topologies. So there are series, shunt series, series, and shunt. So first of all, what we mean by series shunt. So this first word explains the sampling, sorry, mixing, right? So this first word explains the mixing method, and the second word explains the sampling method, right? So in the first amplifier we mix series and sample in parallel, right? So you know that what do we mix in series is voltage. So here what we do is we mix the voltage so that the input is a voltage, and we sample parallelly. That means the output is also a voltage. So this is an input into this amplifier. We feedback structure, we give a voltage and we get a voltage as output. So this is a voltage amplifier, right? And in the next one we mix parallel, so that's a current, right? and we sample in series, so that is also a current to current or a current amplifier, right? And the third one we mix in series, so that's a voltage as input, and we sample in series, so we give a voltage as input and we get a current as the output. So this is called a transconductance amplifier, right? So this is a transconductance amplifier. Similarly, in the final one we give a current as the input and we get a voltage as the output. This is a trans resistance amplifier. Okay, so to further analyze these different feedback types, we need the knowledge of these small signal models of transistors. So here we have the small signal model of the BJT transistor. So we have an input resistor here, which is R5, and if the current going through the base is IB, this current source is beta IB. So this is the output resistance, is the R out. So in most of the cases we can neglect this because of since this is very large, the current going through this is very small. So, and this is the MOSFET small signal model. So we have the gate, source and drain. So gate and source are disconnected because now that in a MOSFET the current going into this gate is 0, right? So this is VGS voltage, so this induced current is GMVGS here, and this is R0, as similar to before, similar to BJT. We can neglect that in most of the cases. Okay, so first of all, let's take a look at this series shunt feedback topology. So that is actually voltage amplifiers. So this is a general structure of a voltage amplifier. So this upper part is actually the amplifier, and this lower part is a feedback network with the feedback factor beta, and the open loop gain of this amplifier is A. So you can see that input voltage this amplifier will be amplified by a factor of A. So if we take a look at this here, we can see that we have sampled the output in parallel. So we have connected this in parallel, so we do take the output voltage and we get a portion of that multiplied by beta, right? So here we do the sampling, sorry, mixing. So mixing is done in series, so we have connected this VS source and beta V naught source in series, so it will generate an input VI, right? Right, so let's try to find an expression for the closed loop gain of a voltage amplifier, right? So the closed loop gain is denoted by AF, and AF is given by the output voltage divided by this source voltage, right? The input voltage, so it is V out divided by Vs, right? So let's try to find this. So V out is, since there's no current going through this network, I can write V out as A times Vi, right, using this, right? So we need to find Vi. So Vi is actually, if we write the Kirchhoff's voltage law, we can write Vs equal to Vi plus beta times V out. So actually Vs minus beta V naught is equal to Vi, right? So we can substitute it here. So then I can write V out equal to A times, here instead of Vi I can write Vs minus beta V naught. So if I simplify this and take V out to one side, I can write 1 plus A beta times V out is equal to A Vs. So we want V out or Vs, so if we do the simplification, I can write AF, which is V out or Vs is given by A divided by 1 plus A beta. So this is the closed loop gain of, this was the closed loop gain of a general negative feedback structure as well, right? So this is the closed loop gain of a voltage amplifier. Okay, so we have calculated the closed loop gain. So apart from closed loop gain, there are two other important parameters, input resistance and output resistance, that we need to calculate. So earlier I forgot this, so we can simplify this diagram into a system like this, right? So is here the input is Vs, so this is our time drawing now is the closed loop system. So this is the input resistance RIF in the closed loop. This is the closed loop input resistance, and there's a voltage source here, dependent source, whose voltage is given by AF times Vs, and here we have the output resistance of the closed loop system ROF, right? So, and this is the output voltage, so we need to calculate the input resistance, closed loop gain, and also the output resistance in a feedback system, right? So let's calculate the input resistance. So before we go into this closed loop system, in the open loop system, if we consider the input current is II, we can write an expression for Ri using the Ohm's law. This is Vi divided by in the input current II, right? So if the input current this is II, since this is a series topology, we can write that this input current is also II, right? So RIF can be written as using this, it is Vs divided by II, right? So let's try to take an expression for this in terms of Ri. So you know, from the feedback system, we can write Vs equal to Vi plus beta V naught, and we know that V naught is equal to A times Vi. So using that expression, I can write Vi equal to V out divided by A, right? So altogether Vs can be written as we can substitute it here. So Vs can be written as Vi plus A beta Vi. So if we substitute it in this expression, I can write RIF is equal to Vs, which is, I can take Vi as common factor. This is 1 plus A beta divided by II. So Vi over II is Ri. So using this, I can write that the input resistance of the closed loop system is Ri times 1 plus A beta. So we can see that the input resistance of this closed loop system has increased. It is multiplied by a factor of 1 plus A beta. So in a voltage amplifier, it is a good thing, it's a desired result that the input resistance is increased, because when the input resistance is increased, there is less distortion to this input signal. So that means the amplifier draws less current from this source, so that makes it less distortions at the input, right? So this is the input resistance of a voltage amplifier in general. Okay, so the next part is to calculate an expression for the output resistance. So in this case, there are some slight differences when it comes to calculation. So here what we do is, first of all, we are going to make this Vs 0. So that means we are removing the source, or in other words, we can simply short circuit this voltage source, and so there will be no source. And also what we do here is we are going to connect a voltage source at the output, whose voltage is Vx, and so it will give a current through this Ix, right? So our output resistance will be given by Vx divided by Ix. So this is how we are going to do it. And okay, so let's do this. So how do we do this? So here we have Vx, Ix, so we need to find Vx in terms of Ix. So that's the easiest way. So if I take an expression for Vx here, Vx can be written as Ix R naught plus AVI, right? So what about Vi? So here Vs is 0. So if we write Kirchhoff voltage law to this cycle, we get Vi plus, so this V out is now Vx in fact, so this is beta Vx, so this is equal to 0. So that means Vi is equal to minus beta Vx. So using this, we can write Vx is equal to Ix R naught minus A beta Vx. So if we take this Vx tends to one side and take a common factor, we'll get this. So in the end, you can write ROF, which is Vx or Ix. So we can arrange the terms here. So you will get R naught divided by 1 plus A beta. So you can see that in the closed loop system, the output resistance is reduced by a factor of 1 plus A beta. So this is also a desirable result in a voltage amplifier. So the lesser output resistance will give the amplifier the ability to give a much more higher output current, so that the output voltage waveform will not distort, right? So this is the output resistance expression. Okay, so now I'm going to work out an example, a voltage amplifier, and let's see how we can calculate the these closed loop gain, input resistance and output resistance. So this is our circuit. So we have a MOSFET here and RD resistor, and this is the feedback part R2 and R1. So you can clearly see that we sample this voltage in parallel using R2. So since we sample it using R2, R2 should be a higher value because it's parallel sampling, and we are mixing it in series using this MOSFET, so which does this addition, subtraction part. So R1 should be small because we are doing series mixing. So first of all, let's see whether this is a negative feedback system. So how do we find that? So first of all, this is Vs and this voltage here will be Vf. So this voltage here is Vf. So if we find Vi, Vi will be equal to Vi is equal to Vs minus Vf. So this voltage minus this voltage. So now if we can show that both Vs and Vf have the same polarity, we can see that this is a negative feedback. So to find out that, what we do is, let's suppose that there is an increase in Vs, the source voltage, right? So if the source voltage increases, what will happen is that the voltage here Vt would also goes up, because if we increase the voltage here, the current going through this will reduce, right? If we increase the voltage, the current going through this will reduce, so that causes a lower voltage drop over here. So that means Vt, and you can see that in this topology Vt is equal to V out, so V out will increase in that case. So when V out increase, you can clearly see that this Vf is taken across a voltage divider. So when V out increases, Vf also increases. So you can see that an increase in Vs will cause an increase in Vf. So both Vs and Vf are of same polarity, so they will be subtracted. So this is a negative feedback system. So I forgot this, that there's an additional thing given here, is that R1 plus R2 is much larger than RD. So that's an important thing, right? So first of all, to work this problem out, let's draw the small signal model of this uh, system. Okay guys, so first of all, let's draw the small signal model of this amplifier, right? So first of all, what I'm going to do is draw the small signal model of the transistor. So we know this is a MOSFET, so it's a current source, and this is the source terminal, and I'm going to draw the gate terminal on this side for the convenience, right? So this voltage is VGS, then there is that output resistance, so that output resistor is also there. So I think we can, I said we can neglect this, but I'm going to draw this anyway here. And this is the drain terminal, right? Okay, so this is how the transistor looks like. And now I'm going to connect other things. So for the source terminal, this voltage source is going to connect there. Vs, and ground it here, and the output will be taken from the drain, and also this RD also connects to drain. And since this VDD, the voltage source, will ground in short circuiting the small signal model, I can have it like this. So this is RD, and here we have the feedback network R2 and R1. It connects to the gate. So this is the small signal model of this amplifier. Okay, so there are two methods to solve this kind of problem. So I'm going to discuss both the methods here. So this is the first method. So in the first method, we are going to calculate open loop parameters such as open loop input, open loop gain, open loop input resistance, open loop output resistance, and also the feedback factor beta. So when we calculated that, we can calculate the closed loop gain, closed loop input and output resistance using those things, right? So first of all, I'm going to calculate the open loop gain. It will be given by the output voltage divided by the input voltage Vi. So in order to do this, I have to make some changes here. So I'm going to remove this feedback network since I'm considering the open loop gain. So I'm going to remove these two resistors, and also I need to make that feedback voltage Vf0. So I'm going to ground this, right? So now let's see how we can do this. And also I can neglect this resistance as well, because this is a very large resistor, so current going through that is very small, so we can neglect that too. So it is a very simple network now. So if I consider V out is actually the voltage across RD. So the current going through this is GM VGS. So V out is minus GM VGS times RD. And VI, or the input resistance, input voltage, is the voltage here, right? So input voltage VI is actually given by minus VGS. So therefore the open loop gain A is GM times RD. So this is the open loop gain. And if we can find the open loop feedback factor, so here we know that this is Vf, so I can write an expression for Vf. So the current going into this is actually 0, because this is the gate. So Vf is actually R1 over R1 plus R2 times V out. So we know that beta, or the feedback factor, is given by the feedback voltage divided by the output voltage, that is Vf or V out. So the feedback factor here is R1 or R1 plus R2, right? So this is the feedback factor. Now since we know both these things, we can easily calculate the closed loop gain. So we know the expression for the closed loop gain in a voltage amplifier is A divided by 1 plus A beta. So therefore the closed loop gain of this amplifier will be given by GM RD divided by 1 plus GM RD R1 over R1 plus R2. So this is the open closed loop gain of this amplifier. Okay, now let's calculate the input resistance of this closed loop system with using the open loop input resistance. So in the open loop system, if this is the input current, so this is the input current, so the open loop input resistance is given by VI divided by II. So input resistance divided by the input current. So you already know that input resistance is input voltage is actually minus VGS, and input current is this current, but in opposite direction, so this minus GM VGS. So therefore the input resistance on the open loop system is 1 over GM. So using this we can calculate the closed loop input resistance. So I think if you can remember, we derived an expression for that for a voltage amplifier, which is Ri times 1 plus A beta. So we know A, we know beta, and we know Ri. So closed loop input resistance is given by 1 over Gm times 1 plus R1 over R1 plus R2 times Gm Rd. So this is the input resistance of the closed loop system. Okay, now let's calculate the output resistance. So we know that when calculating the output resistance we have to do some changes. So actually we have to introduce a voltage source here, and the output which is Vx, and it gives a current Ix into the system from the outside output. And also we have to make the source 0. That means, in other words, we have to so we can ground this point, right? So that is simply that. So now output resistance R out of the open loop system is given by Vx over Ix. Right. So if I see this VGS, what is the value of VGS here? So looking at this, you can clearly see that this is grounded and this is grounded, so VGS is 0. So VGS 0 means that the current through this, so this current is 0 because it is given by GM VGS. So therefore there's nothing here, so it's just this RD resistors. So simply we can write the open loop output resistance is equal to RD. So actually if we consider this that parallel R out resistor here, the actual output resistance will be simple R out in parallel to capital RD, but you know that simple R out is very large when we compare it with RD, so we can approximately say that this is RD, right? Okay, so now using this we can find an expression for the output resistance of the closed loop system. So ROF is equal to R out divided by 1 plus A beta. So we know what is 1 plus A beta is, so using that this will be RD divided by 1 plus R1 or R1 plus R2 times GM RD. So that is method 1 using open loop parameters, how we can calculate the closed loop parameters. Okay, so let's now move on to the second method. So in the second method, what we are going to use is we are going to use the closed loop system and calculate the parameters straight away, right? So in this case, so if you take V out, so you can print, you can directly use the definition. So we say the closed loop gain will be V out divided by Vs, right? So let's see how we can find that, right? So V out here, so the thing that we can use here is this one. So R1 plus R2, this is much larger than RD. So in that case, we can consider that there's a very small current going through this, right? So this current going through this branch is approximately equal to 0, so we can neglect that, right? So neglecting that, we can write V out as, so this whole current passes through this RD resistor, right? So V out is minus Gn VGS RD. So this is using this assumption because this current is very small, right? So that is V out. So if we do not take this assumption into account, this has to be RD in parallel with R1 plus R2, right? Okay. So using this, now let's now try to find Vs, right? So voltage here is actually Vf, right? So we can find Vf. So Vf is taking this network R1 over R1 plus R2 voltage divider, right? So R1 plus R2 into V out, right? So if we take Vs by Vs is actually we can find it using this VGS. So VGS can be written as Vf. So it is the voltage here minus the voltage here. So voltage here is Vf minus voltage at this point is Vs. So what we need to find is Vs. So Vs is actually Vf minus VGS, right? So we want this ratio to be found. So if I can find both Vf and VGS in terms of V out, so that's it. So like that, right? So here Vf is R1 over R2 plus this R1 plus R2 times V out. So what I'm going to do is I'm going to write this R1 over R1 plus R2 times, instead of V out, I'm going to write I'm going to write V out, so V out here, and here instead of minus VGS I can write V out divided by GMRD. think it's clear to you, right? So now I can take V out from this and I can get the ratio what I want. So if I take a common denominator and get the answer, so this Vs is equal to V out times this is R1 over R1 plus R2 Tm RD plus 1 divided by Tm. Right, so then you can see that V out over Vs is reciprocal of this, right? So closed loop gain A is PMRD or 1 plus R1 over R1 plus R2 into GMRD. So this is the answer. Okay, now input resistance. So closed loop input resistance can be written as Vs divided by II, right? So the input current. So I think we found Vs earlier. So Vs can be written as Vf minus Vts, and input current is actually minus GMVTs. So we have to get rid of this VTS thing. So we know that Vf is R1 over R1 plus R2 times V out, right? So V out is actually minus GMVGS times RD. Right? So this is minus GMVGS times RD. And this is minus VGS, and the denominator is minus GMVGS. So we can cancel out minus VGM in both the numerator and denominator. So what I'm going to left out with is 1 over Gm times this is 1 plus R1 over R1 plus R2 times Gm RD. So this is the expression that we got earlier from method 1. Okay, so finally let's calculate the output resistance. So we know what the adjustments to make. We need to add this voltage source at the output, and also I have removed the source and grounded it. So now we can proceed to find this. Okay, so ROF can be written as Vx divided by Ix. Right. So how do you find Ix? Right. So Ix is actually can be written like this, right? So Vx divided by Rd, it's the current going into Rd, plus we can neglect this because of this assumption that R1 plus R2 is greater than RD, much larger than RD. So this we can neglect the current going through this. So that will leave us with the current source GM VGS, right? So here to find VGS, so this is 0, so VGS is equal to the voltage at this point, right? So this is Vx over Rd, and for VGS I can write the voltage here, which is R1 over R1 plus R2 times this voltage here, which is Vx, right? So I can take Vx out from this, and I need this ratio, so it is very easy, right? So Ix is equal to Vx times, this is 1 over Rd plus R1 over R1 plus R2 times Gm. So simplifying this, I can write R out of the closed loop system, which is Vx divided by Ix is equal to, so if I take common denominator, that is Rd, so I have to get the reciprocal, 1 plus R1 over R1 plus R2 times GMRD. So that's it. So this is also the previous expression that we got from the open loop parameters.